In this video, we propose an online, incrementally constructed guiding vector field for navigation in complex environments. Existing autonomous navigation frameworks are already capable of navigating in complex environments. However, these methods cannot effectively resist external disturbances. Let us look at this block diagram. Current frameworks usually adopt a separation between high-level trajectory planning and low-level control. The rationale behind this design is to ensure that both planning and control can operate correctly. However, this also means that the execution of the trajectory lacks feedback. If the low-level controller encounters an external force and fails to track, the planned trajectory may collapse. This is the open-loop problem. Naturally, we would like to transform planning into a closed-loop process. A typical closed-loop idea is the guiding vector field. It generates guiding vectors based on a reference trajectory. This allows the robot to continue along the trajectory when it is on the path and to return to the trajectory when it deviates. Thus, state feedback of the robot is reflected in the high-level planner. Nevertheless, existing guiding vector field methods are limited by trajectory representations and related factors. They cannot be incrementally constructed in unknown and complex environments. Therefore, in this work, we propose a novel vector field navigation method that enables real-time construction of guiding vector fields in unknown and complex environments. We design an incremental and hybrid navigation framework that effectively integrates high-level planning with low-level robot control. Here we present a simple illustration of our workflow. First, we generate a reference trajectory in the environment using trajectory optimization. Next, we discretize this trajectory and mark the corresponding trajectory space as occupied, while the remaining space is marked as free. We then apply an Euclidean distance transform on this space to obtain the Euclidean sign distance field. Based on this field, we can naturally obtain the normal vector of any point in space with respect to the trajectory. At the same time, by applying a second-order polynomial fitting to several nearby points on the trajectory, we obtain the tangent vector. Finally, we derive the guiding vector field shown on the right. It is important to note that the trajectory here is planned online in real time. Therefore, the guiding vector field is also constructed online in real time. In the first simulation scenario, we designed a random obstacle field. We can see that in multiple trials, the robot successfully navigates to the goal point based on the vector field. In the second simulation scenario, we designed a complex three-dimensional environment and increased the flight speed of the robot. The algorithm still performs very well. In real-world experiments, we used a quadrotor equipped with a lidar and a camera. We set up 4 test scenarios, namely wind disturbance, human intervention, dense obstacles, and outdoor environments. In the wind disturbance scenario, we conducted multiple tests. The results show that the closed-loop vector field can resist wind perturbations during navigation. In the human intervention experiment, we tested the robustness of the algorithm. During the flight, a person randomly pulled the robot to prevent it from flying. However, due to the closed-loop design, even though the robot was forcibly dragged away from the trajectory, it was still able to return to the trajectory and continue navigating. In another scenario, we increase the flight speed of the quadrotor. The results demonstrate that our method maintains excellent performance even in unknown complex environments without external interference. Finally, we carried out large-scale outdoor experiments. The method continued to demonstrate robustness and strong real-time performance. In summary, we propose an online, incrementally constructed guiding vector field for real-time navigation in unknown complex environments. The method generates guiding trajectories, discretizes the trajectory space to construct the vector field, and combines ES-DF-based normal components with polynomial-fitted tangential components. The system can easily achieve 20 Hz on edge computing devices. This enables robots to navigate autonomously while remaining robust against wind and human intervention. Extensive simulations and physical experiments validate its robustness and real-time performance. Thanks for watching.